In this video, I'm going to demonstrate the use of the algebraic properties of logarithms for manipulating algebraic formulas and also for doing a couple of different calculations. So first, just to recall, logarithms have the property that ln applied to multiplication of u by v comes apart into ln of u plus ln of v. You can also run this the other way. If you have ln of u plus ln of v, you can put that together into ln of u plus v. Ln of u divided by v comes apart into ln of u minus ln of v. Or if you happen to have ln of u minus ln of v, you can put that together into ln of u over v. Finally, if you have ln of v to the m, that comes apart into m times ln of v. Likewise, you can run this one in reverse, and if you have m times ln of v, you can put it together to get ln of v to the m. Let me show you a couple of calculations that you can do with this. So first, here's a brief summary of those rules. And now I'm going to show you how the calculator actually does certain calculations. Let's suppose that you want to calculate 3.5 to the power 1.2. How does the calculator actually do this? Well, to give you some explanation of why this is an important thing to think about, is that if I had 3 squared, I could interpret that as 3 times 3 and get 9. But 3.5 squared, well, that's going to be 3.5 times 3.5. That's maybe a little bit more work. That turns out to be 12.25. But then 3.5 to the 1.2, how am I going to accomplish a fractional power? Normally we think of a power as being repeated multiplication, but if instead of a whole number of multiplications we have a fraction, what do? Well, there's a way to use logarithms to actually make this work. So let me show you this. I'm going to apply ln to both sides. So ln of y is equal to ln of 3.5 to the 1.2. Sorry, I put the parentheses in the wrong place, 1.2, like that. So ln of this left equals ln of this right. A little too far there. Undo. Okay. Now I'm going to look at my properties and apply this one to the right-hand side. So take apart the right-hand side. That gives me ln of y equals, the v is the 3.5 and the m is 1.2. Okay, so 1.2 times ln of 3.5. Right. Let me just show you. Right here is the v, and right there is the m, and ln of v to the m comes apart into m times ln of v. Now I'm going to apply the natural exponential function to both sides. I'll do it in 2 steps just so that you see everything that's happening here. What I've done there is say that e to the left is equal to e to the right. And again, you have to be careful that everything that should be up in an exponent is indeed up in an exponent. Otherwise, you're going to end up in a mess. Now over here, e undoes ln, and we're going to be left with y equals e to the 1.2 times ln of 3.5. What this means is that if you can program a calculator to compute logarithms, base e, and the natural exponential function, then you can use this to calculate fractional powers by going through this kind of derivation. And just to show you here, let me switch over to the calculator. So ln of 3.5 is that crazy number, 1.2 times ln of 3.5, so it's that crazy number. And again, looking back at the calculation we need to do, I need to apply e to the result of 1.2 times ln of 3.5. Where did my calculator go? There it went. Okay, so here we go. E to the power of 1.2 times ln of 3.5. And what comes out is that number, 4.4965. Again, where I was going with this is that I wanted to calculate this, 3.5 to the 1.2. Let's see if we did. 3.5 to the power 1.2. And there you go, same result. So the point of this is that the algebraic properties of logarithms make it possible to program a calculator to do things like calculate fractional powers. Now, as to how do you program the calculator to do logarithms, that's a long story that I don't have time to get into, but that's what you have to do basically to get these fractional powers calculated. Let me see here. Okay, so there's that calculation. Now let me grab this, keep it handy, and copy it, and we'll move it down the page. Boy, how many of these things am I going to get? Let's try this again. Okay, grab my handy dandy note sheet there and move down the page. Okay. Next, I'm going to do some take-apart exercises. You will see these in the homework. The instructions are kind of long-winded. You'll see a problem like this. So ln of x to the fifth times y to the third, and it'll say use the algebraic properties of logarithms to rewrite this so that the result doesn't have ln applied to multiplication or division or an exponent. So basically it wants you to take apart this algebraic expression. I've given it the name z just so that I have equations to write. Sometimes that's just a little easier for explaining things. Okay, so there's this, and our goal is to take this apart. Okay, so first, looking at the order of operations, we work inside parentheses, so we do this much first, exponents happen, then multiplication and division, there's only multiplication. Now we've handled everything inside the inside the parentheses. The last thing is the function ln applied to the thing in parentheses. Right? So what you need to do is look at this and think of ln of stuff as being sort of a single layer, a single operation. In fact, when you use the electronic homework, there's a button that produces that kind of template, and then there's a space where you can um, fill in something here. So think of that ln as being the outermost operation, an operation all to itself. It is not ln times, it is ln applied to. Now, given that the thing that it's applied to has multiplication as its outermost operation, that means we need to use, well, which property of logarithms? We've got three to choose from over here. Which one are we going to use? We'll use this one because ln applied to multiplication is what we're seeing over here. Okay, so let me get back to my dark blue. I need to use the right-hand side, and u is the x to the fifth part, and v is the y to the third part. So ln of u, x to the fifth. So I've written out this much. Now I write the plus, and now I need to write ln of and put the v in there. That's the y cubed. Okay, so that is one step of taking apart this algebraic expression. Now I have ln applied to x to the fifth. Okay, which one of these properties can I use to take apart ln of x to the fifth? This one. I'm going to use v equals 5, and sorry, I wrote the arrow in the right place and then wrote the wrong thing. I want v equals x, and then I write m equals 5. I'm going to use m equals 5. So now, when I take apart ln of x to the fifth, I'll write m 5 times ln of, and then v is x. Okay, so I have rewritten this part of z. Now let's look at the other thing here. I'm going to rewrite this and put it here. It has kind of the same shape, right? We have ln, the function ln applied to the number y cubed. Okay? So again, of the key properties over here, which one can I use to take apart ln of y to the third? Yep, it's this one again. This time, v is y, and m is 3. So remember what I said about this kind of formula and using symbols as pronouns? Just like you might use it for 5 different things in a short conversation, you can reuse symbols when you're using these pattern matching rewrite rules. Okay, so I need to rewrite ln of y to the third. I'll write 3 for the m, multiplication, and then ln of, and for v, I'll use y. At this point, we have ln applied to plain old x and ln applied to plain old y. There's no more structure. So that's as far apart as this formula will go. So we started with ln of x to the fifth times y to the third. We converted this multiplication into addition of logarithms, and then we converted exponents into multiplication of logarithm by a number. Okay, so this is the final answer, and I believe that in the online homework it will ask you to type in something like that. Okay, so that is the first example of taking something apart. Let's do another one. Take a minute, pause the video, take a minute and see if you can take this apart, and then look at my solution. Okay, let's take a look at this. Z equals ln of the square root of x times y to the fourth. And just in case it's not clear, that is a dot. That's multiplication. And again, we are supposed to take apart. Okay, well, for starters, I find it very helpful to rewrite a square root using a fractional exponent. Do you remember what to do? If I have square root of stuff, I can write that as stuff to what power? Power 1/2. So I'm going to rewrite that square root as power 1/2, and then everything inside the square root has to go inside the parentheses. There's actually several ways to proceed with this. I'm going to show you actually two different ways. So first, the outermost operation is ln. ln is applied to something where the outermost operation is an exponent. So of the rules over here, which one can we use to take apart ln of all that stuff to the 1/2? It's this one. And for this, v is all the stuff inside the exponent, and the m is that 1/2, the actual exponent. So when I start writing out the replacement, I'll start with the m, which is this 1/2, then the multiplication, then ln, and then inside ln, I'll write this v. Okay, so we've just handled one layer. Now we need to see what we can do with this substructure. We have ln applied to something. What is the outermost operation in here? Okay, remember the exponent happens early and the multiplication happens after the exponent. So the multiplication is the outermost operation, and we should think of this as ln applied to x times y to the fourth, and focus on it being ln applied to multiplication of. Okay, given that we've got that structure, of these rules, which one can we apply? This is the one that has ln applied to multiplication. u is equal to x, and v will be equal to y to the fourth. Now we do have to be a little bit careful here because there's a 1/2 times out in front of all of this, and I can't lose that. So I need to do 1/2 times and then put all of the replacement for this right here in parentheses, and you'll see in a minute why the parentheses are necessary. So let me grab my little reference card here and slide it down the page. I need to use that equation. I'll write ln of u, so ln of x, plus ln of, and v is y to the fourth. Okay, so now we've handled another step. The ln of x isn't going to come apart anymore because ln is applied to just x. There aren't any other operations. However, ln applied to y to the fourth, there's something else we can do with that. Let me erase a few lines here. This ln is applied to y to the power 4. So of the equations here, of these three properties of exponents and logarithms, which one can we apply to ln of y to the fourth to take it apart? That's the one we want to use. We're going to match v with y, and m will be 4. Okay, now again, there's some structure here that we want to be sure not to screw up as we do this next step. So I need 1/2 times, and inside the 1/2 times I need ln of x plus. Then again, looking at this rule, I need to write m, which is 4, times ln of, and the v is y. If I now write this a little more fluidly, I get 1/2 ln of x plus 4 ln y, and the 1/2 is applied to the whole group. That's one way of solving this problem. Now, again, in the homework, this is what you would type into the box. I do want to show you, though, there's an optional step you can do, which would be to distribute multiplication by 1/2 over the addition. And that would take us to z equals what? One half times ln of x plus, well, 1/2 times 4 times ln of x will be 1/2 times 4. That's 2. I'm sorry, that's ln of y. Okay. So that's a little simpler, maybe a little easier to type in. Okay, so far so good. But I wanted to show you a second way to do this problem. Let me bring this down here again. So a second way to do this one. The algebraic rules of logarithms are entirely consistent with all the other rules of algebra. I'm going to go back to this form, ln of 1/2 power of x times y to the fourth. Now, you should remember that if you have multiplication inside a power, so power m of a times b, that you can distribute the power and write a to the m times b to the m. This should bring back memories of the algebra test. If I apply that here, I'm going to leave the ln wrapper in place, but I'm going to replace the 1/2 power of x times y to the fourth by distributing the power 1/2. That will give me ln of, and now I do the replacement here, x to the 1/2 times y to the fourth to the 1/2. Now you may be a step ahead of me if you remember that we also have a rule that a to the m to the n simplifies into a to the m times n. I can apply that rule and simplify y to the fourth to the 1/2, and the result will be, well, all the rest of the structure has to be carried along. Y to the fourth to the 1/2 becomes y to the 2. Now, since we've done a couple of these already, I'm going to kind of fast forward through the steps, but I encourage you to pause the video, work with this form of z, and see what you can do. Okay, first thing is to handle ln applied to that multiplication and take that apart. Ln of x to the 1/2 plus ln of y to the 2. And I'm going to have to move my card again. And there I have used that rule. Next, I can change ln of x to the 1/2 into 1/2 ln of x using that rule. Plus, now I'm going to change ln of y squared using that third rule again to get 2 ln of y. And you'll see that we actually ended up in the same place. It's just in one place we did some algebra after doing all of the logarithmic transformations, and in this one we did some algebra first and then did the logarithmic operations. So there you go, two different ways to do that problem. Let's do one more. I encourage you to pause the video and give that one a try, and then start the video again and see how I solved it. Okay. Once again, we need to look at this and understand the structure. And as a matter of fact, let me see if I can get this to work. No, that's not going to work. Okay. So first, we work inside parentheses. We work inside the numerator of the fraction. That's in its own parentheses. And then there's parentheses there. So there's deeply nested parentheses. That means that this is a deeply nested operation, that's subtraction. Then this exponent is applied to it. And I'm not going to draw the box around the 2/3, but the 2 divided by 3 happens up in the exponent, and then it's this base to the power 2/3. There's also an exponent 2 over here, and then it's actually written as a dot that there's multiplication. Okay, so then there's that layer. Underneath the fraction, There's the square root, which will turn into an exponent. And then inside that, we again have effectively parentheses around the x squared plus x plus 1. The squaring happens first. There's no multiplication, but then we have addition. And all of that happened inside the parentheses, and the ln is applied to that. So you can see we've got a lot of structure. Oh, I forgot, yeah, and I even forgot to draw this, the box around the big fraction bar. So there's a lot of structure in this. What we should do is, again, work very much like we do when we're taking derivatives, and work one layer at a time from outside in. So let me do this, and I'm going to go ahead and rewrite that square root as power 1/2. Okay, now again, our goal is to take this thing apart. I'm only going to draw the ln box, and then this division is the last thing that happens out of all the stuff inside. Okay, now looking at the rules, which rule applies? This one. ln of division comes apart. So here we go. Z equals, let me get the orange pen back again. All right, so the U is equal to all this stuff on top, and the V is equal to all this stuff on the bottom. I need to write ln of U minus ln of V. So ln of the top minus ln of the bottom. Okay, so Z equals ln of U, that's the whole top, x squared times 3 minus x, ooh, I made that too big. 3 minus x, yeah, just move the parenthesis there to the 2/3. Minus ln of, so ln of V. So all of this stuff on the bottom. That's x squared plus x plus 1, and again I have to move my parenthesis to the 1/2. By the way, especially if you're working on narrow-lined notebook paper, don't feel any compulsion to try to squeeze everything into just one line of notebook paper. It's not worth it. Math notation is two-dimensional. You need space for fractions and for exponents and for big parentheses and things like that. Use as much paper as you need to do these problems. And this app is even better because I have infinite paper size. So I'm not even killing any trees doing this. Okay. Now we've got two places where the logarithm is applied to something. Let's focus on the left part first. What is the outermost operation in all of that stuff? It's this multiplication. The stuff in parentheses happens early, then the exponent applies, this exponent applies, and then finally the multiplication. So we need to think of this as ln of left times right. Okay, of these rules, which one can we apply? This one. That's ln of multiplication. So there's the left, which is u, so u is equal to x squared, and v is the 3 minus x to the 2/3. Yeah, let me actually just come down here and write this a few rows down. So again, I'm going to write, oh, I got to move this again. See, if we were really in a classroom, I would write this stuff on the sideboard and I wouldn't have to keep moving it around. Okay, I need, and you'll see why in a minute, I need that parenthesis, or at least why I'm writing it. I need ln of, so ln of, and for u, I need this u, which is x squared, plus ln of, and for v, I'm going to replace it with all of that stuff. I need a bigger parenthesis. 3 minus x to the 2/3. And all of this is the replacement for ln of product of x squared and 2/3 power of 3 minus x. I have more to do. I'm going to, for the moment, just copy this and catch my breath. You'll see in a minute why I wrote these parentheses. They're not absolutely necessary, but they are kind of helpful. Okay, let's look at this thing next. Again, there's ln applied to something. What is it applied to? Well, there's all this stuff here in parentheses, and then there's power 1/2. So we need to think of this as ln of power 1/2 applied to something. Okay, looking at our rules, of these rules, which one can we apply over here? Yep, this one, ln of a number to a power. Okay, so this time the base is everything except for the power 1/2, and the m is the 1/2 in the power 1/2. Okay. So the next step, I'm going to have to, well, copy all of this down without making a mistake. That's going to be so much fun. ln of x squared plus ln of 3 minus x to the 2/3 minus, and now I'm going to use parentheses and replace this with all this stuff here in parentheses. Okay, I need, let me look back here at the rule and show you, I need to write the m times ln of, so times ln of, and then replace that v. It's x squared plus x plus 1. Now, is it clear what's happened? That from here, I've had to do a couple of different steps, and in one I replaced all of that part, and then in the second step I replaced all of that part. Now, technically I don't need these big square parentheses. You can see that if you drop them, the result is actually still correct. However, sometimes when you do these logarithm replacements, you can see that you're going to get something that has addition or subtraction in it. And in those cases, it may be very important to have parentheses so that the entire replacement formula is incorporated into the rest of the formula for z. For right now, however, I can just simplify this. And just kind of flatten it. Like that. Okay, now we've done these a couple of times, so from here on out, things are fairly straightforward. I hope you understand how to do this take apart now. that comes apart into 2 ln of x. And then if I want to take that apart, that comes apart into 2/3 ln of 3 minus x. And I'm going to leave the rest of this in place. Okay. Couple of things to notice at this point. We still have ln applied to some stuff. Right there we have ln applied to subtraction. And over here we have ln applied to, this time it's addition. So there is an exponent over here, but the ln is not applied directly to the exponent. It's instead applied to addition, and one of the things that's being added happens to be the square of 2. This is a very important thing to notice, which is that ln of, say, a u plus a v does not come apart. Ln of u minus v also does not come apart. Just for comparison, let's go back over here and look at the equations that do let us take things apart. Ln applied to multiplication, that is something that you can take apart, and there's addition in the result. Ln of division comes apart, and there's subtraction in the result. Ln of an exponent comes apart, and there's multiplication in the result. But none of these rules have an ln applied to addition or ln applied to subtraction. It's just the case that ln applied to addition and subtraction, there's just not much you can do with it. And so this formula that we've ended up with here, that's as simplified in the sense of take apart as we can do for this particular function z. And so this is what you would type in into the electronic homework, for example. Okay, so lots of explanation there, some simple examples, a couple of different ways to do these things, and some complicated examples. And you can see now why you have to be very comfortable with the properties of exponents, the properties of roots and converting between exponents, fractional exponents and root notation. You have to be able to look at a big formula and see all of that nested structure, because for taking apart expressions with logarithms, you have to work outside in very much like you do with taking derivatives. And the question, of course, well, what rule do I apply? Well, you have to look at the equations that hold for the natural logarithm, figure out which one you can match, and use that to take something apart. And what tells you which one of these to apply is that you have to look at the outermost operation of the stuff inside ln. Okay, so this is the take apart technique for using properties of logarithms on to rewrite an algebraic expression.